the next workshop. The next workshop we have is on accelerate static verification of queues and complex design at RTL as well as the static Netlist stage. Right. So for this session, we have two speakers. Speaker Ravindra and then we have second speaker Francis, right? So let me introduce both of them. So Ravindra holds MS degree in electronics science from University of Pune. Ravindra has experience of more than 20 years in EDA domain. He has major expertise in static verification and design and debug. In his spare time, Ravindra loves nature photography and traveling. The next speaker is Francis Chokalingam. Francis Chokalingam is a master engineer at Broadcom in the processor engineering group of ASIC product division. He has around 23 years of work experience in the semiconductor industry, and he has worked for Intel and Honeywell before joining Broadcom. In his spare time, Francis enjoys science fiction and cycling. So with that, let's get started. Video rolling.
Hi everybody, all of us know design teams are looking for efficient method to catch as many as design issues and as soon as possible to meet the tight project timelines. For huge and complex designs, there are certain challenges. Flat level SoC runs for multiple iterations within practical runtime are not feasible. Due to huge runtimes, traditional hierarchical approaches compromise on the quality on design analysis. Importantly, designers need to review millions of violations to arrive at few important ones. Through this workshop, we are introducing a methodology for efficiently signing off huge designs for static verification. This methodology is applicable for RTL as well as Netlist designs. This methodology is targeted for CDC, that is clock domain processing, as well as LP, that is low power checks. This workshop is jointly presented by Synopsys and Broadcom. I would also like to acknowledge contributions made by NVIDIA team towards this workshop, with sharing their experiences about the methodology. In today's workshop, we would be looking into challenges associated with verification of huge and complex designs. We would be going through various designs to understand the specific challenges associated with static verification for huge and complex designs, to address important aspect of performance requirements, typically runtime and memory consumption. We would be going through details of sign-off abstract model, also known as SAM flow, for reducing designers' debug pains and debugging the actual root cause. We will understand machine learning based root cause analysis, also known as MLRCA flow. I will share NVIDIA's experience with SAM flow. Here we would see the characteristics of the huge SoC that use this particular methodology. We will review the traditional method used and performance results shared by NVIDIA team. To share Broadcom's experience with MLRCA based analysis, Francis from Broadcom will present the details. I will introduce Francis as workshop advances. We would have question and answer session after concluding this workshop. Let's understand various challenges design teams face with static verification of huge designs. Please note, in general, with huge designs, we shall not restrict the scope of this methodology to SoCs only. New age subsystems, up to a certain extent, some of the IPs are also becoming huge and complex. This methodology is applicable for those type of designs too. All of us know the design size are increasing over a period. Requirements of new features, solutions has triggered increase in design size. Growth in new features being added to the design is causing project teams to validate the design from various domains of static analysis. Surge in multiple clocks, resets is demanding validation of CDC and RDC checks for each and every design being signed off. Need for performing various domain analysis brings the situation of huge number of messages, which in turn causes heavy usage of waivers also. Conventional approach like post-processing huge reports and then manually reviewing it causes real bugs to miss. This is an error-prone approach. There is need of performing multiple runs in short possible time and improving designers' productivity. This necessitates flow having capability to perform static verification for huge designs. To achieve low power targets, design teams need to perform low power related checks. With growing number of instances, voltage and power domains, low power checks also throw similar challenges for huge designs. Impractical runtimes for flat runs, QR differences with respect to the reference results are some of the hurdles for concluding low power checks. Even if full flat runs are complete with known performance challenges, designers are served with another set of problems. Managing and debugging thousands, sometimes millions of violations. Analyzing so many violations and finding out the actual issue is really difficult task. This brings the necessity of feature having capability to report actual root cause of the problem. So, how design teams are addressing requirements associated with huge designs? Let's review certain traditional flows being followed by design teams. We know full flat approach ensures quality of results as sign of quality results. At the same time, most of the runs end with impossible runtimes, as well as project team need to wait till the complete design is available for validation. This challenges causes delays for design sign-off timelines. One of the known flow used by designers is to black box certain IP subsystems in the design and perform the static verification. This flow helps in having very less runtime as well as less memory consumption. On the other hand, debugging of issues as well as structures is impossible due to no visibility inside the logic due to black boxing method used. Black boxing also causes many design bugs to miss during the verification process. Designers cannot use this methodology for sign-off. Another flow used by design teams is to use interface models for IP subsystems causing performance issues. This helps with limited visibility around interfaces, but QR is compromised. The traditional flows causes delay in design sign-off. Yet, there are design teams with great difficulties manage to generate the results and reports for their designs. I need not to repeat the particular pain points as well as challenges they go through to arrive at the successful set of results. Next hurdle for the design teams is to review the reports, find bugs and resolve it. Methods like generating reports based on IPs are being utilized. Possibility of two or multiple designers debugging the same root cause is very common. Two independent IP designers would not have any visibility into the issues caused by missing SOC perspective. Post-processing of text reports with using different scripting language is also followed. Methods like segregating the reports based on IP instances are common. Finding out a real design bug is always a difficult achievement with these approaches. Importantly, these approaches require in-depth knowledge about the design before ignoring or waiving or even filtering out any violations. These approaches are difficult to maintain in long run. I believe all of us are now aware with challenges associated with huge and complex designs for static verification. To address those challenges for the design teams, let me to introduce new method using sign-off abstract model, also known as SAM flow. Okay, in earlier slide, we have already went through known limitations with traditional approaches. Let's understand how is SAM flow better than the traditional flows. We know flat run causes huge run times. Black box does not ensure QR. Also, ILM-based flow supports limited visibility around the interfaces. As compared to all these methods, SAM flow enables the static verification with reduced amount of logic relevant for the static check, as well as it gives visibility into the internal structures for debugging of the issues. As the intent is captured from the actual RTL design, SAM ensures that QR is maintained till the sign-off stage of the project. Before we learn how does SAM flow work, let me to remind you that SAM flow is applicable to clock domain crossing as well as low power checks too. At block level, designers would have necessary design and power intent, that is UPF, available. After performing the low power checks and reviewing results, sign-off abstract model needs to be generated by VC Spyglass. You can have multiple blocks abstracted. At top level, along with the necessary constraints and power intent, that is UPF, abstracted models are used. Beauty of SAM flow, it does not require interface or dummy or stub files created for the abstracted blocks or IPs. The relevant design intent is captured in SAM flow, with reducing a lot of additional tasks for the designer. Like low power checks, SAM flow is also used for performing CDC analysis for huge and complex designs. It enables matching results with flat run, as well as, since this particular QR is maintained, design sign-off is possible with this particular approach. In terms of performance improvements, there is a huge gain observed with reduced runtime and reduction in memory consumption. Traditional hierarchical flow has known limitation with respect to convergence analysis for CDC verification. SAM flow takes care of performing convergence analysis as well as provides visibility into the design structure for debugging it. Using SAM flow, designers are empowered with ability to perform multiple experiments with practical runtimes. Multiple iterations which we are as a design team looking for to perform in practical runtimes, those are possible with SAM flow. No loss of QR and well correlating results with flat flow helps in signing off the design with confidence. Abstracted model contains the relevant logic signal. This allows the designer to debug the issues with great ease. This is definitely different as compared to the black box or ILM based methodology. To support the claims of benefits of SAM flow, here are results generated for different designs. This analysis was done for low power checks. It is evident as compared to full flat runs of different designs having huge run times and memory requirements. SAM flow helps with gaining productivity, reduced compute cost, as well as enabling multiple experiments within practical runtimes. I would like to highlight this specific aspect with respect to SAM, which is reduction in compute cost. As design houses need to maintain the costly compute farms with huge memory for the servers. It is very feasible with SAM flow to allow the design teams to gain much more faster runs within short practical run times. Many designers have seen huge amount of productivity gain with reduced amount of runtime with SAM flow. Again, with SAM flow, we get huge designs analyzed very easily. But what about the analysis of results generated? Designer might have reports running into tens of thousands of, sometimes millions of violations. To address the important requirement of violations debug and root cause analysis, let me introduce a novel methodology, machine learning based root cause analysis, also known as MLRCA. Let's see where designers need to put efforts in completing the CDC verification. In general, the CDC verification process starts with CDC setup and the run. Once the results are available, designers spend a lot of time in analyzing, prioritizing, and then debugging the violations. Most of the precious time is spent on debugging violations. Certain violations require modification in the design, constraints, or tool setup. Many violations end up in the form of waivers and filters, which in turn keeps on appearing for further runs as part of waiver management. MLRCA flow generates report based on root causes automatically. That's the precise value addition done by MLRCA. With MLRCA based reports available, designer need to review the root causes only. This particular approach reduces designers' debug efforts significantly. Many design teams have reported significant gain in debug productivity with this particular approach. In terms of benefits, root cause analysis brings in a lot of efficiency as compared to manual review and debug of the results. Analyzing prioritized clusters or simply set of root causes is easy and fast for designers. Automated clustering and analysis are error-free. With employing debug clues provided, designers gain further productivity with easily resolving the design issues. You must be interested in understanding how does MLRCA improve the productivity for designers. Let's go through high-level working of MLRCA feature. After static verification performed by VC Spyglass, machine learning engine works on the database generated. It analyzes all the violations, finds actual root cause for the issues. It provides the designer with ranked clusters. In turn, designer need to review and debug the minimal set of root causes and not the huge number of effective violations. Here are certain results captured from analysis for different designs. I would like to highlight the number of violations generated without and with MLRCA enabled. Depending on the nature of the issues found in the design, you can easily see noise reduction ranging from 3 to 47 times. This is a huge gain for any designer. Okay, enough of highlighting the results from internal benchmarking. Let's look into some of the real life experiences from esteemed design houses. During recent verification day 2021, NVIDIA presented on topic scaling Netlist CDC verification through hierarchical flow and machine learning with VC Spyglass CDC. NVIDIA team presented their experience with SAM and MLRCA flow during this event. It was presented by Alex Lee, Pratik Porwal, and Pratik Sutar of NVIDIA, while Bhumik Motholia and Harshavardhan from Synopsys were the co-authors. I would like to use certain slides of SAM flow from that particular presentation to share NVIDIA's learnings and their feedback with you. NVIDIA designs are getting bigger and complex. Recent design had gate count of around 3 billion with 1,800 plus clocks. Please note all these are asynchronous clocks. At SoC level, 20 IPs subsystems were integrated. As presented in earlier slides, NVIDIA team also faced the challenges of huge runtime, required machines with terabytes of RAM, as well as heavy efforts to review and debug the violations. NVIDIA team was looking for a methodology that can help reducing debug efforts and improve designers' productivity. For full flat method, NVIDIA team used Spyglass CDC with reusing Netlist design setup, including constraints from timing analysis flow. Known advantage of full flat method is the ability to debug the entire design structure. There were iterations required to clean the design from CDC perspective. When started with full flat method, runtime observed was around 36 hours and memory consumption was around 736 GB. Yes, these are practical numbers captured from their analysis. With SAM flow being used, NVIDIA team first verified all the IPs subsystems and ensured that the IPs are CDC clean. Then generated the sign-off abstract model, used the same SAM files during top-level run, performed SAM-based run, and observed amazing performance numbers. Please note, at this particular flow, they did not went through qualification of abstract models as compared to the traditional or certain hierarchical approaches. You need to perform the block to top validation as well as you need to perform the abstract model validation. SAM flow takes care of reusing this particular abstract model at top level runs and helps the design team to perform SoC level CDC analysis. So let's go through the performance comparison on the next slide. For this particular SoC, as highlighted in the earlier slide, the flat flow runtime was 36 hours, while the runtime for SAM-based flow at top level, including highest runtime for one of the big IP, was around 14.5 hours only. This clearly shows performance gain of around 2.5 times. At the same time, the memory consumption at SoC level run reduced to 212 GB from earlier 735 GB. Feedback shared from this particular exercise. Using SAM flow, design team analyzed the IP and subsystem logic which was relevant for SoC level verification. This reduced the runtime as well as memory requirements for compute farm. No surprises found as compared to the reference results. This was one of the important aspects confirmed with this exercise on real life project, that designers will not need to worry about the QR with respect to their reference results. As part of this workshop, we have Broadcom team sharing its experience with machine learning based root cause analysis. I would like to use this opportunity and introduce you today's co-presenter, Francis Chokalingam from Broadcom. Francis Chokalingam is a master engineer at Broadcom in the processor engineering group of ASIC product division. He has around 23 years of experience in the semiconductor industry. Francis has worked for Intel and Honeywell before joining Broadcom. In his spare time, Francis enjoys science fiction and bicycling. Francis, over to you now.
Thank you, Ravi, for the introduction. Hi, everybody. I'll be presenting the Broadcom's experience with machine learning based root cause analysis feature used for validating one of the recent projects. The design under consideration is a billion-plus gate SoC for machine learning application. This consists of a large array of processing engine, a management CPU, various memory interfaces, PCI subsystem. There is a network on chip connecting the various modules. Then we have the debug and the peripheral logic. The SoC has over 100 clocks in 84 different clock domains. This has around 10 reset domains. The complexity of the clock domain crossing analysis stems from the network on chip interconnect, which is essentially a large number of distributed async FIFO. This is a flop-based memory with granular clock gating. Third-party IP bridges with asynchronous clock domain interfaces also increase the complexity. Design itself being large, doing at the SoC level, the CDC analysis was time consuming. Hence, we started with the block level CDC analysis. The block level CDC analysis was done for 4 complex IP blocks. The partitioning of the complex IP blocks were same as that we had for the synthesis hierarchy. Hence, the initial setup for the VCCDC was seamless using the synthesis constraint. But we did see this setup violation. Hence, the qualifier reset constraints needed to be added to address these setup and integrity issues. These changes to the constraints were fed back to the block level STA constraints for sign-off analysis. The block C here, as you can see, had large number of unsync async reset violations. These were unsynchronized resets inside the design for which the RTL updates were required. And with these updates, these violations were addressed. There were glitch violations, as you can see here, which were on the third-party IP asynchronous bridges, where the signal were held using handshake mechanism. These were reviewed and waived. There were convergence violations in all of our block, which were due to the testability logic as well as network on chip interfaces, where the mutex conditions were reviewed and these violations were waived. Now, looking at the sync CDC violations in more detail, as you can see, there were large number of unsynchronized violations in all these blocks. Analysis and prioritization of these violations is an extremely tedious task. This requires deep understanding of design as well as tool. MLRCA feature was very instrumental in debug and analysis of these violations. Violations were grouped into small number of clusters. As you can see, the block A, C, and D had top 5 clusters had 95% of these violations. These smart grouping provides an effective grouping of violations. Essentially, this arranges CDC violations in a systematic fashion under various clusters. RCA identifies these known cause-effect relationship between these violations. This also provides possible causes and debug clues. There were around 13 possible causes identified for block B and 5 causes for other blocks. Essentially, 70% of violations for block B were addressed using these 9 of the debug clues that were provided. Remaining were either design issue or needed explicit qualifier constraint. Now, looking at one of the CDC violations in more detail, this example shows a sync CDC data path violation. This was debugged to an improper qualifier in the design. Essentially, the qualifier was feeding into the fan-in cone of the destination flop earlier. Hence, it was not actually qualifying the unsynchronized or the asynchronous logic cone. The clue was provided by the MLRCA feature. This helped us in narrowing down this violation more quickly. Required RTL changes were done for the synchronized qualifier to be moved closer to the destination flop. The Verdi-based GUI, which is part of the VC Spyglass, was fast and intuitive for us to debug quickly. Runtime for all these blocks were reasonable. Even for our bigger block, the block C, it was around 6 hours. Even the memory footprint was very manageable. For the bigger block also, it was around 150 GB. Now, looking at the SOC level root cause analysis, we had around 1,800 CDC violations. MLRCA reduced the analyze, debug, fix iteration that we typically go through and avoided reviewing each of these violations individually. So these violations were reduced to the 71 clusters with 82 potential root causes. We got a table with the order of severity wherein the top entries in the table, the top clusters being the root cause of greatest number of violations. Hence, the top 12 clusters in our case contributed to 70% of the violations. Hence, by addressing these root causes with the top clusters being looked at first, large number of violations were able to be addressed in one chunk. In essence, the MLRCA feature for us reduced this debug iterations and hence reducing our CDC analyze time frame. I would like to hand over back to Ravi to continue this workshop. Thank you.
Thank you very much, Francis, for confirming on the designer's pain, as well as different hurdles while dealing with huge complex designs and debugging violations for static verification, and importantly, sharing Broadcom's experience with MLRCA. With this, we are at the last slide of this workshop. To conclude this workshop, let me to summarize the advantages of SAM and MLRCA flows. As we have already seen, SAM flow enables reduction in hardware requirements from LSF compute farms. It helps in performing analysis from the early development stages of the design tool. With utilizing multi-core, multi-threaded runs, the runtime reduces further. With reducing synthesis timing constraints for Netlist designs, VC Spyglass platform ensures reuse of the design knowledge. In addition to SAM flow, MLRCA helps design team with providing root causes of the issues, in turn improving debug efficiency a lot. Automatic generation of constraints to resolve CDC issues is supported with MLRCA. It helps in reducing designers' efforts over developing it manually. Pickle-based environment immensely helps with custom report generation. It also supports object-based waiver generation. So if required during final stages of design sign-off, designer can still utilize powerful pickle-based waivers at final sign-off stage. Both SAM and MLRCA flow uses industry-leading debug environment Verdi. Verdi is integrated with VC Spyglass platform, and many design teams use it for debugging their design issues. That's all from my from this workshop. Thanks NVIDIA as well as Broadcom team for sharing their experiences. Thank you all of you and your time, as well as the interest you have shown in today's workshop. Based on today's time available, now we would like to take the questions. Thank you. Okay, thanks for this question, Lokesh. So in terms of future roadmap, I won't be able to share or comment right now anything, but just to highlight and once again repeat what industry has already gone through this particular pain, as you correctly highlighted, the handling of noise. Okay, and as Francis has also updated in his particular presentation. With CDC, okay, this particular unwanted or huge number of crossings or violations, that is definitely taken care with MLRCA. And as we have seen in those specific numbers or results shared in various results, MLRCA definitely helps the design team to concentrate on the actual root cause of the issue. So even though the techniques are not going to reduce the number of crossings, because that is the actual intent of the design that has been already captured, but the amount of time design teams used to spend on debugging it, as well as ensuring what are the exact root causes they need to analyze and fix, that particular major portion has been taken care with MLRCA engines. And that is the precise guideline or recommendation from our side to any of the particular domain of CDC or even LP, that instead of working on thousands of violations, just work on certain few root causes only.
Perfect, Ravindra. I don't see any questions from audience.
Probably since the lunchtime is nearing,
Very
many
close.
of them have, yeah.
Maybe one quick question to Francis, right? So, I know you've been using the technology for quite some time. For any newcomers, do you want to advise how they need to pick and choose, and where they need to focus as starting to the CDC validation?
Yeah, basically any synthesis setup that we have, it could be directly leveraged. I think that was a primary thing that makes it easy to start running the tool. The focus is primarily, I think, the convergence checks are something that is feasible through SAM model, as well as it is collected in a separate group as part of these violations. So that is some additional advantage. I think that was something that I noticed. I think those are the main things that I saw looking at these tools. And,
okay,
yeah.
Perfect. So I think we don't have any more questions from the audience, so we can maybe sign off for today. Thanks, guys, for joining.
Thank you.
Okay, thanks. Bye. Good day.